Thank you very much, Rob. Yesterday we heard a lot about the demand in the cement industry for new materials, especially in the next 10-20 years. Today we heard some ideas how to bring other slags or untypically slags for the cement industry in this market. And in my presentation I will show you some ideas, some positive and negative aspects of these processes and why it could be interesting to use BOF slag, but not in every way. So first of all, I would start with one slide presentation where I show you what we are able to do in the melting labs. That is where we all, or where we did all the melting tests. I will show you today. So in our melting lab we are able to remelt every slag type under neutral conditions up to 2000 degrees. We can make a conditioning of the slag, a chemical treatment, and we have different possibilities of cooling. So for example, water granulation, where we can change the additives in the water, change the temperature, change the flow rate. We can make a dry cooling, where we are measuring the cooling rate. And we also developed together with Prime Metals, or in former times Siemens VAI, the first steps for the rotating cup system. At the moment there is a pilot plant running at FEhS Alpine, so the first trials in 2 kilogram stage were done in our institute for heat recovery and looking for the quality of the generated GBFS. So I will present you the results from an ongoing research project that's called ProInnoLDS. It's funded by the Austrian funding agency FFG, and the partners is on the one hand the coordinator K1 Met, the Metallurgical Competence Center in Austria, the Steelwork FEhS Alpine, Prime Metals, Scholz Austria, and the University of Leoben. So the primary targets in this project are the reducing of BOF slags to find new markets, to create a hot metal with low phosphorus contents. We heard yesterday in the presentation from ArcelorMittal that especially the phosphorus is a limiting factor to recover BOF slag in the blast furnace or to the sinter plant. Our idea was, okay, when we get a high phosphorus containing metal, how we can reduce the phosphorus content and create a slag with high phosphorus, perhaps to use it as a fertilizer like the Thomas phosphate, and to create a slag for the cement industry. So today my presentation will be about these 2 points, the reducing of BOF slag and the creating as a material for the cement industry. So how is the BOF slag used today? In Europe we have about 11 million tons per year of BOF slags. Therefore in Germany a little bit more than 3 million tons. I showed you here the use of BOF slags from Germany because for this we have very detailed information. Most of it, more than 55%, is used in the construction sector, mostly for road construction. 13% is used as a liming fertilizer, internal use to recover the contained iron. Due to some bad properties or not so good properties, 13% has to be landfill, and small amounts are used in other applications. So what did we do in our melting laboratory? First of all, as I told you, we can remelt slags under neutral conditions. Here, one video how it looks like when we are remelting a BOF slag under neutral conditions at 1650 degree and typically basicity of 3.2. You see this here, it's more or less like water, it's very, very liquid, no problem with the viscosity. So it's very good to handle this material. So the first step in the project was to make a carbon reduction. So we used the carbon crucible for this. The reduction was more or less 100%. 100% BOF slag we used at 1650 degrees also, the same basicity. and there we got some problems. As you can see here, there is nothing liquid in it. We had a lot of problems to get this material out of the crucible, and when you imagine this happens in a steelwork in a big scale at 25 tons, a lot of work, and you don't want to have this. So we try to decrease the basicity and so decrease the viscosity by adding some blast furnace slag, 20% of blast furnace slag. There we are able to reduce the CS basicity to 2.2, but as you can see here, it's more or less the same problem. The reducing of the basicity from 3.2 to 2.2 doesn't really help. So we made a third trial where we add quartz and 10% quartz and so nearly 100% SiO2. So we are able to decrease the basicity significantly to 1.7. Same temperature. We didn't put the slag out of the crucible. We let that cool down in the crucible, and after this we cut the crucible to make this picture. We see here we got a segregation of the metal. At the bottom we got some metal due to the high density, it goes down and were selected there or collected there. But you can also see some metal pieces in the slag. So this means the slag had still a high viscosity. The metal was not able to go down to the bottom, and we had more or less the same. Due to this, we made a further trial where we increase the temperature. So the same basicity like before, but now we increase the temperature to 1750 degrees. That's a little bit untypically, so we have a higher wear of refractory in operational practice. But as you can see here, the slag was in the first moment very liquid, everything okay, but due to the cooling of the crucible when it's out of the furnace, we are below the 1700 after a few seconds. And so we had the same problem, about 50% remains in the crucible, we're not liquid and we don't get it out. So this means in a big scale, when you have a problem in the steelwork and the slag pot has to wait for the further treatment, 1 hour, something like this, you are losing the temperature and you got the same problems. When you're looking to the chemical analysis, it were typical BOF slag and the other one, the blast furnace slag, with iron oxide about 30% summarized, and we decrease this to nearly zero, the oxidic iron. I will show you in the next diagram. It looks like this, or it looks a little bit better. Here the columns are the sum of the different oxidic states of iron. So the silver is metallic iron, then the gray one is FeO, and the black one is Fe2O3. So we are able to separate these oxidation states. The red lines are the CS basicity. It's here on the right side, and you can see due to the simple carbon reduction, we don't really change the CS basicity, but we reduce the iron content. But there's still a lot of iron oxide remaining in the slag. Due to a decrease in the basicity, we, as you saw in the picture or in the videos, we are also decreasing the viscosity, and so the slag is more reactive, and we are able to reduce the iron content more and more. When we are looking to the mineralogy, just very fast, the reference slag that was reduced by carbon without any treatment, we had about 30% tree calcium silicate, so very good for the cement industry, but also 10% free lime. But this slag was not able to be handled in a bigger scale. where we add some blast furnace slag, we got gamma decalcium silicate, so typically for secondary metallurgical slags that it's disintegrating. And when we are looking here to the fourth trial, where we increase the temperature, it was able to handle the slag, but no tricalcium or decalcium silicate, so it's not really useful in the cement industry. So we said that's not really a way that could be fit in industrial practice, so why we don't try to make a GBFS-like material from BOF slag and not a clinker-like material. So what to do? We have to increase the addition of sand. Here's a picture I showed you before, and now we added more than 10% sand. We added 15%, 20, 25. You see the basicity, sure, it decreases, and the slag was very, very reactive, very low viscosity, and we have no iron in it, so everything was reduced. Here you see a short video about the water granulation in our laboratory at this basicity. Oh, it's the sound, okay. There I put the crucible out of the Tammer furnace. It was a mixture here with 50% sand. So for the viscosity it was enough, as you can see. Here when granulating the slag it's very, very liquid, and that's during a longer time. So I think we needed about 30 seconds to granulate this material. It was not a problem in the viscosity, and we got a very nice material that looks like GBFS. So when we're looking to the chemical composition, we started in the first trial with 25% sand to be sure, okay, we are very, very low in basicity, and to guarantee that we have a glass. So we looked to the glass content. It was more than 99%. Everything is good, but with the CS basicity we were below 1. So very, very low, and this means there are bad properties in the cement. So we decrease the addition of sand to 20 and 15%. The glass content remains at a very high level here, but when we are at CS basicity of 1.3, that is typically not a problem in our laboratory to get glassy. We see the glass content is about 0. So what's the difference of this treated BOF slag to blast furnace slag? It's the alumina content. It is very, very low. So we look not just to the simple basicity, we look to the B3, the one especially with alumina. And here you can see we are at 1.5, that is very, very high. And we try to keep this CS basicity at 1.3, but to increase also the alumina content. That was also just one trial to get a glassy material and to look, okay, how it looks like from the cementitious properties. We got 99% glass, a high CS basicity, and with this we go to the cement laboratory. The cementitious properties in the first step, we looked with a 50-50 mixture of a SEM1, okay, how are the compressive strengths of the mortar prisms. You can see here the FEhS monitoring, as my colleague Mr. Ehrenberg said before. That's a monitoring we are doing 2 times a year for every blast furnace of our member states. So we have a big database with the maximum and minimum compressive strength and an average. And here the green line is the quartz sand, so that is the 0 reference. With the first trial, where we got a very low B1 basicity, the compressive strength is very low. It's at or below the minimum, also after 28 days. After increasing it, we are in the range of the minimum, that is like a very bad granulated blast furnace slag, and by increasing the basicity we should get very good compressive strength, but due to the very low glass content there was no really impact on the compressive strength, so that we are here in the area of quartz sand. The last one that where we added also the alumina was then in the range of the average of our monitoring. So we can see here, just with this trial, we are in the average of the Western European GBFS that are more or less good values, especially because we didn't really make a lot of trials to optimize the slag. So a short conclusion and the outlook. Creating a clinker-like material from BOF slag is possible, but unusual high temperatures are necessary for this. Decreasing the necessary temperature by additives decreases also the clinker performance, and increasing the amount of quartz sand followed by water granulation creates a GBFS-like material with relatively good cementitious properties. So what will we do in the future? We will optimize this process in the next time by reducing the amount of additives. We have the advantage that we are coming from the top with the CS basicity, so when we are using less additives we got better cementitious properties. We just have to guarantee that we got a glassy material. So that is the most important thing. And we will also have ongoing or a further project after this one, where we try to investigate the optimal condition. So when we are at about 10% additives, we would be very happy, because that we think is possible to treat in operational practice. And we should also look for cheaper additives and not primary materials, so that this process is not just ecological very good, but then also economical. Thank you very much. If you have some questions, you can ask now or contact me later by email or by phone. Thank you very much.
So thank you very much indeed for a very interesting presentation. You gave us a lot of information there, and I think it shows the way for increasing value of these, if you like, problem slags. Are there any questions from the real world just before we go on to Slido? Okay, we have a couple of quick questions. Are you planning any similar studies for EAF slags?
We already did. Last year on Global Slag I presented our project for EAF slag, where we found out more or less the same, that we are not able to create a clinker-like material because we have to increase the lime content for the EAF slag. The advantage for BOF slag is that it comes with a very high calcium oxide content, so it should be an easy way to go to the clinker, but due to the high viscosity we are not able to handle it. And with the EAF slag we have to increase with lime the lime content, and then we got the same problems like you saw here in the videos. So in the EAF project we also looked more to the GBFS way.
Okay, was there any free lime content in the final slag?
In the final slag here of the GBFS, no, because we are so low comparable to the clinker way with the basicity that we don't have any free lime in it.
Okay, were you able to create a hot metal with low phosphorus content?
No, not when we are reducing 100%. That's a problem. When we are reducing 100%, we got all, or more or less all of the phosphorus in the metal. That's a problem, and this metal is not interesting for any industry. So the casting industry and also the steel industry is not interested in it. but in some other national projects we are looking for part reductions or partly reductions, not just 100%, perhaps 90 or 80% is enough, and then we see that the phosphorus content is not so high in the metal that you can use it later. Sure, then the properties of the slag will be a little bit more poor, but we have to find a midway.
Okay, Doug Haynes asks, will you be able to adapt the Thyssen O2 sand injection process?
No, because then we got all the iron oxidized, and that's not our plan. We try to reduce the iron, so that's the opposite. And when we got so high iron content at, I don't know, 30%, 50%, it is beneficial in the cement, and so it doesn't help. So we try to reduce the iron content, so we don't need oxygen, we need carbon, silicium or aluminium.
Right, just off the top of my head, your additions were, for your final case, was 15% sand, SiO2?
Yes, 14%
and 8 or 9% Al2O3.
Yes.
So are there any waste materials out there which have that composition, that balance?
Sure, a lot of, but in the first...
sorry to interrupt, but it sounds like some clays could be perfectly reasonable in terms of composition.
Yes, but first of all we have to look how we can decrease the amount of necessary additives, because 25% or 20% additives is very, very high. And that is too much handling and a lot of work, so the next step will be to decrease the amount of necessary additives to 10%, and then we will have a look how we can find secondary materials.
What if the additives were exceptionally cheap? As cheap as dirt, as cheap as clay, for example?
It would be good, but also we have to decrease the amount, because when we get so high amounts of cold material in the slag, we need to heat it up, so we need a lot of energy, and we will try to keep the costs low as good as possible. We know it's a cost-intensive process or energy-intensive process, so especially from the addition of materials, we don't want to have so much in it.
Have you looked at all at the possibility of using any other chemicals as a fluxing agent to allow your viscosity to remain high at lower temperatures? So, for example, fluorine minerals have been used.
We didn't look at it because typically fluorine is not really interesting due to environmental properties. So we try to don't use fluorine in any process step in the steelwork. So that is, I think, not the right way, especially not here in Europe.
Okay. Are there any other comments or questions from the floor? Yes, please, Doug.
Dr. Doug Haynes. Hasn't the Merox SSAB process for electrical and carbon reduction of the slag already covered what you're looking at?
That they already did or has this process, or what do you mean?
Yeah, but so essentially taking the BOF slag, adding carbon and adding heat with the electrical input and carbon electrodes, and it achieves what you're trying to do.
And which process is that? Merox?
Merox SSAB.
Merox SSAB.
Yes, but we have to look to the region where we want to implement a process like this, where also perhaps the energy costs are really high. So we will also look if we are able to make a chemical heating, so perhaps to use metallic aluminium, metallic silicium, and to use or to make a reduction that is more or less free of necessary electrical energy.
Okay, yeah, thank you.
Just a very quick check. What temperature would the slag arrive with you, for example, after the BOF, the basic oxygen furnace? When it's poured from the press?
Typically, or what do you mean? When it's set?
Yeah.
it depends on the steel work, but we say it should be below 1700. So we are working, or our aim is to work with a slag of 1650 degrees.
Okay, so it would arrive with you at 1650 degrees. You're talking about only heating it up by 100 degrees to your 1750.
Yes, but as I told, when there is an interruption and the slag pot has to stand 1 hour, and you will have a lot of problems. And to get out of 25 tons of slag, I don't think that is a right way.
I think the steel makers need to pay a lot more attention to their slag. Just forget all of the metal. That's just that's an irrelevant byproduct. And
that's right, yes.
Slag fans down here, forget the metal. Just concentrate on the slag. I mean,
do you, Amir Shakurov, slag recycling, do you investigate some additives that could use it without heat, additional heat for preparing this such of material to reducing of FE content?
Yes, I told we are looking for secondary materials that are rich in metallic aluminium, metallic silicium, and to heat by a chemical way, and not to need a further step like electrical heating. So.
And what is your opinion? It will be cheaper to using of such of these expensive additives or electricity heating for using with using of carbon?
It depends on the region. So when we are in Sweden or Finland, I think the energy costs are very low. There could be the electrical heating more interesting. But for other regions, I think the chemical heating is interesting, but not with primary resources. So you have to look if you find in other industries perhaps secondary materials which you get very cheap and which helps you in your process. And especially the other elements that comes with these materials don't have any negative influence on your process.
That's all the time we have for questions. David, you've answered our points very, very well indeed, and we thank you once again for an excellent presentation. Thank you very much, David.
Thank you.